So I'm going to talk about this rock, okay? It came from Iceland. Now, I'm going to own up to begin with here. I'm a bit of a fraud in that I've never been to Iceland. It's been on my bucket list forever, but I've never actually managed to get there. However, a number of our members have. And they have, so Keith Robbins, Philip Slack and Mark Eller, and they have all contributed images that I've used, photos that they've taken that I've used in this presentation. So I'd like to acknowledge that. You will see this, for example, is from Mark. And you'll see as we go through, when you see the nice images, somewhere on the corners, you will see whose image it is. So given all of that and the fact that they went all over Iceland, I'm going to give you a quick tour of Iceland as well, geologically, and hopefully you'll enjoy it. So the story actually starts exactly this time last year, when I showed you this rock. Now, you may or may not remember it, but it was at the Christmas soiree last year. I'd been to the Outer Hebrides earlier in the year, and I brought some rocks in and showed you some pictures. I showed you the rocks, actually. And this is this wonderfully named pseudo-tachylite, which is a part of the white stuff here is a myelinite from the Outer Hebrides thrust zone. It has been brecciated, broken during an earthquake, and it is cemented by the black material, black obsidian. So it's effectively basalt cementing a breccia, white breccia, but it's basically a black and white breccia. So when Keith was in Iceland, he came across this, which is another black and white breccia. So his perfectly natural question was, is this another pseudo-tachylite? Because that's the sort of name that sticks in your head. Basically the answer is nope. Because if you look at it, although it's black and white, what you have here is finely crystallizing black breccia cemented by the white stuff. So it's black cemented by the white, as opposed to the other one, which was white cemented by the black. So what is it? Oh, no, let's first off say, where did it come from? So it came from Skaftafellsjökull. Now, I should point out that this is a tautology, because jökull means glacier in Icelandic. So basically, this is Skaftafell glacier from southeast Iceland. And there it is. It's a fabulous glacier all the way down, comes around the corner around there, all the way down through here. And you've got all this material, moraines in front of it and everything else. So where is that? Well, it is, well, I'll just show you, it's there. That little bit there, that tiny little arm there, is the Skaftafellsjökull, which is a tiny little arm of the Vatnajökull. And this glacier is, it's very difficult when you're working with Iceland to get an idea of scale. But that glacier is the third largest on the planet, after Antarctica and Greenland. So that is a very big bit of ice. And we are going to look at just this tiny little bit here. So this is the Skaftafell. And there's a whole bunch of these little fingers of ice coming off of Vatnajökull. And in front of it, classically, there's what's called a sandur. So this is an outwash from glacial terrain. It's very, very flat. It's all basically braided rivers, braided streams. And that whole area is called a sandur. We'll come back to that. So, interestingly, this is from 2021. This is the most recent Google Earth image. But it also has, being Google Earth, has older ones. So this is 1984. Same image, 1984. I'm going to flip back between them. So in particular, it's worth looking in this area. Oh God, I've gone the wrong way. There we go. So you can see the retreat, and it's retreating all the way round. So that's your climate change for you, actually in front of you. And this little area in front of the glacier, this Skaftafeljökull, it would only be visible, would only have been there, and this rock would only have been recovered, because that's where it came from, had it not been for climate change and some decent warming. So it came from here. This is Skaftafeljökull again, going up there, the front of the glacier, and these are the moraines, big piles of junk brought down and pushed around by the glacier. And you can see the mountains in the background. If you look down at your feet, then this is what you see. This is the material on the sandur. So all sorts of different rock types you can see in here. Most of it is black basalt, hardly surprising. But there's dolerite in here. There's porphyry over here. This is scoria, which is lava that's got all these holes in it because that's where the gas has escaped as it's erupted. But, oh dear, wrong thing. Mostly well-rounded clasts, not all, but mostly well-rounded clasts on the sandur. And this is a fantastic example of frost shattering of the larger lumps. So we were down here in this area here, and this is the general geology of Iceland. Now, the thing to notice here, and I'll go into this in a bit more detail, not a lot, but a bit more detail later, is blue, blue, green, green, brown and pink. And there's some grey in there as well, grey, grey, and then brown and pink in the middle. And they parallel each other as you go. Oh dear, my thing's falling apart. So if we just zoom in on that area there, this is where things came from. Running repairs. Right, so Skaftafeljökull here. This is where it was picked up from. And all of the pink stuff is this recent Holocene sandur. The white is ice. And what you have here are Pliocene. The blue underlying all of this is Pliocene, so over about 3.3 million years. So somewhere towards this end of the high street. The green, which sits on top of that, Pleistocene, so down to less than 1 million years old. So we're actually coming through the building there. And this stuff, the grey and the brown here, and in fact, well, we'll come back to that. The grey and the brown is probably just outside the door there. It's less than, considerably less than 1 million years old. Then there are these things, the most recent eruptions, these silicic lavas, 11,000 years old. Now, there is underneath here, there's a volcano. And if I could pronounce it, I'd tell you the name, but there is one. And all of the brown and the grey here, and where it says hyaloclastites and pillow lavas, these all of this was erupted underneath glaciers. So during the Pleistocene, the whole of Iceland was covered in ice, and so but the eruptions kept going. So there was a lot of glacial eruption, and that caused the formation of pillow lavas and these things called hyaloclastites, more of which later. So back to our site, this is a moraine, and you can see big lumps of angular stuff that have been moved by the glacier, dumped there, glaciers moved back. Presumably this is another dump from the glacier. So lots and lots of stuff. And that's the Sandur going off, that plain going off down to the coast. The mountains at the back from that geological map, those are Pliocene lavas. That whole stack of lavas is all Pliocene. And if we go and look at that wall, this is basically what we see. Pleistocene valley wall, lots of lavas, lots of erosion going on there. But also, and the interbeds as well in between these things. But there's also, you can see this red over everything. There's alteration going on, that's hematite, and that's a fairly typical bit of weathering of recent basalts. And now, this may be, I haven't been here, obviously, this may be my imagination, and in fact, it may just be snow. But if you look at these bits of white, which do not seem to be on a flat surface, I think this is mineralization, which is interesting. So back to our geology. As I say, the blue, Miocene, Pliocene, the green is the Plio-Pleistocene, then you've got late Pleistocene coming through here, and then post-glacial lavas. So since the end of the last ice advance. Now, it's interesting that the oldest bit of bedrock on Iceland is 16 million years old. The youngest bedrock we have in this entire area is about 35 million years old, and you have to go up to Cobham for that, or to the AE3 M25 interchange to get to the Bagshot Sands. So the whole of Iceland has formed since that period. It's all really very young indeed. So anyway, what is the rock? Back to the rock. So the black here is fine-grained. It certainly looks like basalt. Iceland's made of basalt, basically, so that seems like an eminently reasonable assumption. It's highly brecciated. It doesn't fit together. It hasn't been sort of frost-shattered or something. It's not in place or anything like that. So it's a collection of highly uneven chunks of basalt. Now, I'm going to say that this is a hyaloclastite because I think that's what it is, but it's not the sort of hyaloclastite I was talking about before, but it's related, okay? So remember the name, hyaloclastite, and I will try and demonstrate what it is. So this is 2 weeks ago. Down in the southwest corner of Iceland, there have been eruptions. There have been 7 eruptions this year. This is the most recent. This is a road that goes to the Blue Lagoon, or used to. This, interestingly, is a berm that they put, that's the rest of the road there. That berm they erected to divert lava flows from the Blue Lagoon. And there's also a power station over here as well. And this column of smoke And I realised this column of smoke is the road burning. No smoke from anywhere else, just where it comes along the road and burns up the tarmac. So anyway, what is a hyaloclastite? Well, by definition, it's a volcaniclastic breccia formed by non-explosive fracturing, so it's not, when things are blown out, and the breakup of quenched lavas. And fragmentation of that lava occurs in response to thermal stress imposed on the outer parts of lava flows while the inner part of it is still moving. So underneath glaciers, subglacial eruptions produce hyaloclastites because basically the lava comes up and hits a glacier and it gets chilled instantly. But the lava is still molten immediately underneath, so you get, that keeps moving and you get over the top of it, you get these broken up breccias. But even on, well, I'll come on to that. Now, the majority of lavas in Iceland, I'm sure you've all heard of Pahoehoe and lavas. So Pahoehoe are very fluid lavas, are very viscous, and they move slowly, but they break up. The majority of lavas in Iceland are somewhere in between those two things. They're what's called rubbly Pahoehoe, which is a bit of a cheat. So this is the recent eruption. This is Pahoehoe. So you can see it's flowing, and you see these flow, don't know what you call them, but sort of skin on the surface. Basically, it's like skin on a custard. And then around the back of the vents, you obviously get all of this, which is spatter cones. This is where you get a lot of the scoria, which has got all of those holes in it, where lava's come out of here and it degassed and then fallen down onto here. But at the front of the flow, this is what you see. So this is the rubbly Pahoehoe, where you can see it's cold here. This is ice and snow on the ground and previous deposits. And this is gradually moving along. So the inside of this is still fluid. It's moving. The top is being chilled by the air and then is breaking up. So what you end up with is layers of, when it solidifies, stops and solidifies and cools, you get a layer of basalt. I say that, could be this, could be, whatever. But the top has this brecciated top. And that's very typical of the lavas in Iceland. And that brecciated top, that's hyaloclastite. So, what sort of basalt is it? I mean, there's basalt and there's basalt. Well, we know that Iceland's in the middle of the ocean and middle of the Atlantic. And so, it's a mid-ocean ridge basalt, or MORB, which is a lovely name. And we know as well, of course, we've got all of this going all the way around. This is where that earthquake was. That tiny little thing in there is the Juan de Fuca plate, which was that tiny little fragment of an old plate that's left there, and the big earthquake was just there. So more mid-Atlantic basalt. I've shown you this before, but I do like to bang on about this really. Spreading rates. They're quite variable. This is East Pacific, this is the Indian Ocean, and the Mid-Atlantic Ridge, a whole variety of different measured rates, but basically slower than these other ones. But the thing I like about this is that this is the rate at which your nails grow. And this is the rate at which your hair grows. So the next time you trim your nails or bite them like I do, just think that is the distance that America has moved away from us in the time that it took for that to grow. Although at the moment it seems to be moving away from us in much faster. So this is the classic model for generation of oceanic crust at mid-ocean ridges. So you get a bit of mantle partial melting down here due to passive decompression as things pull apart. And you get sort of magma here and lava flows and rifts and da-da-da-da-da. But there's something very wrong with that as far as our rock is concerned. Anyone like to hazard a guess? Something fundamentally wrong. Well, it's not just no ice, there's no land.
Doesn't Iceland actually have a sort of non-visible continental chunk underneath it?
No, no, I'll come to the structure and stuff in a minute. No, the point that's wrong with that is that Keith picked it up. Here is a rock. And as you can see, that's 3,000 meters of water. So the whole point, if I went back to the map with all the mid-ocean ridges, they're not called mid-ocean ridges because they're on land. They're in the middle of oceans. So to have picked this up, it can't be just ordinary mid-ocean ridge basalt. So why? Well, because Iceland is what's called a hotspot. So this track that you can see here is supposedly the track of a hotspot that came up underneath Greenland about 70 million years ago. And basically, the hotspot means that the area has tracked across a mantle plume. I'll explain that a bit more in a minute. And that is now situated under the mid-Atlantic ridge, under Iceland. In fact, it's actually in the southeast of Iceland. And that is the reason that Iceland is an island and not just a bit of very submarine ridge. Its basalts are chemically enriched from the mantle because you've got deep mantle upwelling, so you've got different chemistry in there. So it's enriched, so it's called E-morb, as opposed to N-morb, which is normal morb, or D-morb, which is depleted morb. So enriched mid-ocean ridge basalt. And what that means is, so this is pretty much the picture I showed you before is pretty much that bit up there. But this has a contribution from way, way down in the lower mantle and possibly down at the core boundary. Chemically, they're distinct. So this is the range of chemical values. These are a whole bunch of elements all the way along here, the heavier elements. And that's E-morb. This is N-morb, normal stuff, and a bunch of other ones from other places. So quite distinct. Quite distinct. So let's talk about this. So here is our a plume rising from it. So something happens very deep down at the core mantle boundary, and you create a heat pulse that produces some melting, and a plume rises up through the mantle. That brings fluid, liquid, and heat, a lot of heat, right from the inside of the Earth. So it comes all the way up, and when it hits the surface, what you get are flood basalts. You may have heard of flood basalts, but basically they cover a big, long area. They're almost certainly one of the causes of mass extinctions because they go on for a long time, they cover a lot of area and produce a lot of of gases. So that's pretty much what happened under Greenland about 60 million years ago. There's flood basalts on the west and on the east of Greenland. This is squeezed back together. So, and then you've formed the ridge, you've got spreading going along through here, but this is 25 million years ago, Miocene, and you've still got some heat coming up through here, so you get the Iceland plateau. And that's because basically, although the plume itself has probably gone, which is why we're not getting flood basalts anymore, what you do still have is this tail, which keeps coming up and pulsing and producing, and in particular, bringing heat to the surface. So the current situation is like this, plume-generated crust in this sort of area through Iceland. So what that means is that you've got this amazing pattern of basalt across the whole area. So the original flood basalts were here and here, but then you've got the whole Faroe Island plateau all the way down here, and basalts all the way across here. These are equivalent, and then it's just being narrowed down to now it's just on Iceland. This is the Reykjanes Ridge and the Koblenski Ridge going off to the north of Iceland. And along those ridges, you get quite a lot of seismic activity. It's hardly surprising. There's lots and lots of, particularly along the fracture zones along here and up here, but in fact all the way along the ridge and through Iceland. So Iceland is actually pretty seismically active. This is a map of just the earthquakes this year, since the 1st of January up until a couple of weeks ago. And there are 30,000 earthquakes there. Now, in all fairness, most of them are less than magnitude 2. In fact, most of them are less than magnitude 1. And most of them are actually not, big earth movements, but associated with magma moving underground. And they tend to cluster before eruptions. And there have been 6 eruptions in Iceland this year during this time, all of them down in this area here. It doesn't mean that things aren't moving around elsewhere. So, can we see them? So this, I've shown you this before, this is our detectability of our Raspberry Shake with distance along here in thousands of kilometers and earthquake magnitude. And Iceland's about here, about 1,900 kilometers away. So to be able to see anything, it would have to be about an earthquake, a magnitude 5 or above, preferably above. Now, in all of these earthquakes, this is, as you can see, this is a bar chart of it, 0.5, 1, 1.52. There is only one quake that's bigger than magnitude 5. And I think it's that, which frankly is pathetic. So that, it does have the attributes of an earthquake, although there's an awful lot of noise around as well. So we don't see them because they're all far too small. But if you live on Iceland, you do see them. So this is 2 days ago. And this is just, once again, this is a Raspberry Shake on Iceland. And this is what they see. So all of these little things here, these are all, and that bigger one, these are all earthquakes. And probably a lot of this other stuff is as well, but very, very small. So lots of activity, lots of things moving around. So there we have it, most of it going on along here with the eruptions, but as I say, other things underneath the glacier. There's the glacier there, up this road here, and then a couple over here. Why there? Well, because that's where the boundaries between the plates are. So you have the Reykjanes ridge down here. This is the Koblenski ridge, and then and this basically comes down here and overlaps the Reykjanes ridge, and then there's a zone in between which gets quite a lot of seismic activity, and some of the biggest volcanoes are here. So Katla and Hekla are around in this area. This is Surtsey off down here. It produced different, very, very different lavas from the basalts elsewhere. So that's the general pattern. You've got essentially the mid-Atlantic ridge runs down through here, but it's offset in Iceland. So you have this volcanic, what's called the Eastern Volcanic Zone, the Northern Volcanic Zone, and then this is where the current eruptions are going on. And you'll remember from the pictures you saw and from any of the pictures you've seen this year that these come from fissures. They're always fissure eruptions down here, and they're all in this orientation, and they're all offsetting and going off down into the Atlantic. So the terrain underneath it looks like this, basically. So the highest areas are in here, and you've got this, the volcanoes are in this area, there's other volcanoes up here, but essentially you've got this whole chain of things going on, and this offset as you go across from here up to here. And there's this funny little bit in between, which is sort of its own plate, really. It's all lavas, but it's basically you could argue that it's part of the Western plate, or indeed the Eurasian plate, the North American plate or the Eurasian plate. And this is it. So if you stand on the North American plate and you look west, no, you look east, this is what you see. So this is across this broad area, and in the distance here, that is Europe. Well, it's the European plate, Eurasian plate. And in the front here, you've got all of this broken up and rifted terrain. And it's quite dramatically rifted. So this is literally the edge of America, of North American plate at any rate. It's not active, or they wouldn't have a nice path and tourists going along it. The activity is well away, but it is very dramatic. And, you know, because Iceland's full of these sorts of rifts and also has glaciers and big rivers, it, not surprisingly, also has waterfalls. This is one of the biggest, Gullfoss. It falls once, twice, and then there's another one down here, and it makes an awful lot of noise. So I'll show you some more. So this is a completely unpronounceable waterfall and valley. So it comes down through there and then goes off down there to the coast over there. And that means Feather River Canyon. So I'm going to call it Feather River Canyon or Godafoss. I'm sure that's not a D. So it's probably pronounced in a different way. But Godafoss, lovely waterfall. Gufufoss, you get the idea. Foss is a waterfall or fall. Okay. And Skogafoss. Wonderful. Okay, that's your waterfalls. So that's Thingvellir, Gullfoss, Skogafoss, Gufufoss, Godafoss. It's lovely. But before we go back to the rock, I just want to take you over here to Kirkjufell. I'm sure I'm getting this all wrong. But anyway, I'm going to take you there because if you've ever watched Game of Thrones, you would probably recognize this. This is the most photographed mountain in Iceland. It's called Kirkjufell, and there are fabulous pictures of this online in different weather conditions and with the northern light behind it, and also it is incredibly beautiful, but it's also a complete con. As Mark showed, this is the standard witch's hat view of it. Nice half a U-shaped valley, but actually, if you look at it from the side, it's a ridge. It's an arête between two U-shaped valleys. So not half as dramatic from that side as it is from the end. But the view from the top is terrific. Absolutely beautiful. Here are our U-shaped valleys, so all cut out by ice during the last ice advance. So, back to our rock. We've talked about the black stuff. What about the white stuff? What is it? Well, I'm going to jump to an answer. They're zeolites. Now, zeolites are very common in Iceland. They are I'll just read it, hydrous silicates of sodium, calcium, sometimes potassium. What that means is that they have a crystal structure and then they have water separate in it, held within the crystal structure, but not part of it, which means that they can indeed lose that water and then regain it if they get dry or warm or whatever. They are very common in Iceland, zeolites. At least 20 different types are recognized. And they're generally white or colorless and really difficult to tell apart, unless you have really good crystal forms. So if you can see the crystal forms and that sort of thing, then that's fine. But the only way you'd figure out exactly what this is by using XRD. But now I hope you can see this. If we look up here, particularly around here, around there, around there, around here, what you can see, and when you see the rock itself in enhanced specimen, it is incredibly difficult with this rock. It is a black and white rock. It is very difficult to really focus in on things and show things in contrast. But this is radiating fibrous structure, and so is this, all the way around here. And then this is much more massive, and there's a slight difference in color, maybe. So I would say that there's at least 2 different types of zeolite in that rock. Again, you can see they're growing into voids here. One of them is fibrous and radiating. The other one looks massive, but it might just be things end on. What I'm going to say is that these are zeolites. And the reason I'm going to say it is because they're the commonest zeolites. And they also happen to be radiating and fibrous. So for me, and having gone through the book, Icelandic Rocks and Minerals, and looked at all the pictures of the zeolites. These are the most likely. So scholasite and mesolite. This is calcium aluminium silicate. This is sodium calcium aluminium silicate, and this is that water that sort of sits in the structure but isn't part of it. They all have specific gravities of about 2.25, bit more, and they're quite pretty. Now, the interesting thing is that back in 1960, this is a picture from the 1960 paper by George Walker from the Journal of Geology. And it's brilliant. This is hand drawn. And what he did in eastern Iceland was that he went around and sampled, this is the actual terrain, okay? And he went around and he mapped out the lava flows and he mapped out the surface and he identified the zeolites. And he found that there were different zones of zeolites, that you had a mesolite, scholasite zone, you had a chabazite, thomsonite zone. At the top of what had been the original top of the lava pile, because these were parallel to the original top of the lava pile, not the current one, it would be zeolite free. So what that says is that this is a picture from eastern Iceland, thousands of meters of lavas piled up on top of each other. And in the lower part of this, you would get scholasite and mesolite, and then different ones higher up. Following on from that work, it was extended below into the subsurface with drill holes, and they found that the zeolite zones continued as you went down, having different zeolites as you went deeper and deeper. So the mesolite scholasite zone basically goes from sea level up to about 800 meters. And they form from the interaction of hot geothermal waters in the surrounding basalts at temperatures below 230 degrees. They're quite cool temperature. I mean, that seems hot, but and there's plenty of hot water, geothermal waters. This is where it comes out of the ground and you get steam coming off of it. It's boiling, and this is the secret lagoon being enjoyed. So in an attempt to try and work out the mineralogy of these things, I measured the density of the rock, just simple weight and displacement. And I was a bit surprised because the density of this rock is only about 2.35 grams per cc, which is way too low for a rock that's 70 to 80% basalt, which should be 2.9 grams per cc, with zeolites around that sort of number. In fact, if it was just basalt and zeolite, it would have to be less than 20% basalt, or contain a great big vug, which would be 15% of its volume. And I can't see any reason why I would believe that. So I looked a bit closer. So when you start getting your eye in it, the more I looked at this rock, the more complicated it became. It was really annoying. I thought I had a nice, easy task here, but... So first of all, there are rims around most of the clasts. So you can see those little rims around there. And that one, believe me, it doesn't really come out. It's very difficult, like I say, in black and white to take, black and white rock to take pictures with color, but that's red. That's a hematite surface. In some places, you've got these apparent growths where things have begun to grow around the edges of the clasts, more rims up here. And there's a difference between something like this, which has this reddish hue, and the rest of it, which is very dark. Now, this is a paper from 1982, where somebody went out and looked at the weathering rinds of basalts and andesites in North America, and showed that as you went, so this is the surface of the rock, this is 6 millimeters, that's 6 millimeters, that's about 10 millimeters into the rock. This is the chemistry. So it did lots and lots of these detailed analyses. And what you can see is that most of it, most of the chemistry disappears, drops away, aluminium drops away, silica drops away. And the thing that builds up is the iron oxide. There's our hematite again, forming those rims. So this is a hematite rim, basically, or hematite-rich rim. Now, again, very difficult to show, but most of these clasts, particularly here, well, all of them actually, all of the black clasts have been eroded more than the surrounding zeolites. They are, I recommend you come and have a look at it, but when you look at it, all of the black bits are a bit more hollow than the surrounding zeolites. Now this is, we were assuming that this was basalt. Now, basalt's good and hard, you make cobbles out of it. And it's usually about 5, which is the same as the zeolites. So why have you got differential erosion of the black material? So I would say that most of these clasts have actually been altered. And I think that they are actually mostly elephane, which is an amorphous fine-grained clay mineral mass, really, and clay minerals, except for some. So this, for example, stands proud. This reddish bit, I think that is probably a representative of original basalt, and that the rest of this has actually been altered. And yet, again, you get your hand lens out and you start seeing things. Damn it. The clast, and you see 3 of them here within these, have hexagonal, glassy, dark red crystals with indistinct cleavage. And the only thing I can ascribe these to are garnets, which are present in Iceland and form by thermal metamorphism, where your lavas have been close to like a vent or an intrusion for a long period of time. It doesn't just happen, it has to be there for a while for these things to form and grow. And that has to be hot above 300 degrees C, and that's a lot hotter than any of the zeolites can stand. So they must have formed before the zeolites. So maybe somewhere like this. This is Haverfeld crater. So presumably in there, while all this was forming and stuff were coming out, that kept hot for a very long time. Or maybe something like this, where you've got a lava tunnel and you've got hot lava going pulsing through one of these underground. We talked earlier on about the seismic activity and the movement of lava. And this is how it moves around. And presumably the walls of somewhere like this get hot for a long time. So let's try and put all that together and try and understand the history of this rock, because it's complicated and because almost all of this you can deduce just from the fact that we've got it here. So the first is that sometime back in the Cretaceous, there was a mantle plume that started to rise from the core mantle boundary and started working its way through the mantle. In the Paleogene, that plume reached the surface, producing flood basalts under modern Greenland and the Faroes. Possibly contributing to the breakup of the North American plate from the Eurasian plate. And that's hotly debated. During the Miocene, the plume tail is still rising now. Causes uplift of flood basalts at the mid-Atlantic ridge itself, which forms Iceland. As things spread apart, you get Iceland left there. The oldest rock that's there at the surface is 16 million years. So this is Iceland, 16 million years. Then during the Pliocene, probably, the basalts associated with our rock erupted in a rubbly Pahoehoe flow and became buried beneath a thick sequence, thousands of meters of lava flows. The basalt clasts formed as this pyroclastic top of a viscous lava flow, breaking up to produce the porous breccia. And we believe that in that area, there's at least 1,500 meters of lava flow. But that burial is either near a vent or maybe an intrusion, which means that the temperature must have been kept above 300 degrees C for long enough for the garnets to have formed. Then, at some stage, presumably during the Pleistocene, it cooled and you got water flowing through and all that sort of stuff. It had been uplifted, so maybe there was air as well, oxygen, blah, blah, and you got weathering and the formation of the rines, including the hematite. Following on from that, you had the geothermal water circulation at less than 230 degrees, depths of about 1,000 meters from the top of the pile, and that caused metasomatic breakdown of the basalt to allophane, that's my guess, and the precipitation of the zeolites within the mesolite scolecite zone on top of the weathering, and it filled the porosity. Now, quite a lot of this is hypothetical. It's my guess. The only real way of knowing some of these things, like allophane and mesolite scolecite, I think it's a reasonable assumption, would be to cut it up and analyze it. Best way to do that would be XRD. But things haven't finished yet. So sometime during the late Pleistocene glaciations, the Vatna Glacier, or one of its tributaries, carved valleys into these piles of lava. Bear in mind that during the periods of ice advance, the whole of Iceland would have been covered by glaciers. Our rock was likely part of a bigger bit. I'm told that the reason that this piece was brought back was it was the only bit that would go into Keith's pocket or rucksack or whatever. There were other bigger bits around. So it probably started off as part of a bigger bit, probably produced by ice plucking and or freeze thaw on either exposed valley sides or subglacial. Then you've got transport. So it's come from somewhere up underneath the big glacier, and transport either on, in, or indeed under the glacier itself, delivering the rock to the moraine, to one of the moraines of Skaftafellsjökull, possibly all subglacially. And then finally, during that transport process and from the moraine, it was then reworked. It was picked up from the Sandur. So it had been reworked from moraines. And it had obviously been water eroded, rounded. It's a rounded cobble. And obviously the black material has been eroded out bit more than the white. So it ended up on the glacial outwash plain to be picked up by Keith and brought to us. So that's the history of our rock. But I have one final question, which I will just leave it open to you. What is it? Thank you.